Continuity. Objectives. By the end of this lesson, you should be able to explain what it means to be continuous on a graph, use the three-part definition to show continuity at a point, list the known continuous functions, list the types of discontinuities and their graphical representations, and apply the laws and properties of continuous functions. Before we get into the formal definition of what it means to be continuous mathematically, I want to think about what the word continuous means. So in everyday speech, continuous means having no breaks or interruptions. So if you were to say someone is continuously reading a book, you would think that they weren't going to stop for anything, that they weren't going to get up and get a drink of water, that they're going to do so for an entire amount of time without stopping. So if you're trying to decide intuitively whether a function is continuous, well, the way we represent functions is by a graph. So you can ask yourself, can I draw this graph without ever lifting up my pencil? Because if you had to lift up your pencil, you'd have to stop and take a break. There would be some interruption in the flow of your graph. So intuitively, that's how I want you to think about the notion of continuous given some function. Let's take a look at an example. So we have f of x equals sine x. Sine x is this basic function that goes through 0, 0 and has this wave pattern, right? It oscillates back and forth. And graphically, it would appear that sine x is a continuous function. So if we think about this in formal definition, once we put our pen down on the paper, if we can draw the entire function without lifting back up our pencil, then we're continuous. So we know that this is going to go on and on and on and on forever, and I never have to lift up my pen or pencil to keep drawing the function. So this appears to be a continuous function. But to get a more precise definition, we have to decide whether we're continuous at every single point in a function's domain. So now we've reached the three-part definition of continuity at a point. So we're going to suppose f of x is some function that's defined on an open interval containing c. Then f is continuous at c only if all three conditions below hold. So the three conditions are, number one, that f of c exists or is defined. So in other words, when I substitute c into the function f of x, I have to get out a number. That means that the function is defined or exists at c. The second thing I need to happen is I need the limit as x approaches c of f of x to exist. So I must show the limit from the left equals a limit from the right. So in order for a two-sided limit to exist, I need the limit from the left to equal the limit from the right. And then finally, I need the limit as x approaches c of f of x from part 2. I need it to equal part 1. I need it to equal the function value when I substitute in c into the function. So let's kind of draw a picture to talk about why we need all three conditions to hold. So we'll start out by looking at the hypothesis. So f of x is defined on an open interval containing x equals c. So let's go ahead and create our point c and our open interval around c. So the first part says f of c has to exist. Alright, so let's get another color. That means when I substitute c in, I have to get out some value. So that's my filled in circle. So here's my f of c. So I've satisfied part 1. f of c exists, or it is defined. So when I substitute it in, I get something out. Part 2 says that the limit as x approaches c of f of x has to exist. So as I approach c from both sides of c, my function has to get closer and closer to the same value. So what if I go ahead and draw my function to look like this? So here, I've satisfied the hypothesis. F of x is defined on an open interval containing c. So here's my open interval. I'm defined everywhere. So I'm defined here, here, here. At this point, I'm defined down here. And then I continue and I'm still defined over off on the right side of the interval. So I'm defined on the entire open interval. F of c specifically exists. So when I plug in c, I get out f of c. The limit exists. The limit as x approaches c, it's whatever this value is, let's call it L. So the limit exists from the left side, from the right side, they're the same number, they're L. But notice that I don't have the limit as x approaches c of f of x equals f of c. So that means that the limit in part 2, L, has to equal f of c, the function value. Because if I do that, I'll close the gap. So the way that it currently stands, we'll use a different color. If I went to go draw this function without lifting my pen, I'd keep going, I'd stop, and I'd have to jump over this gap to continue it, and then go back and fill in the circle if I wanted to draw this graph. So the way it currently is, it's not continuous because I've only satisfied parts 1 and 2. So in order to be continuous, I have to move this point, so let's kind of cross it out, I have to fill in the gap. So I have to make this now f of c. So part 3 really says that parts 1 and 2 have to be equal to each other for there to be continuity at a point. Alright, so in this example we're going to use the three-part definition on a pretty basic function just to kind of see how it works. So the question is f of x equals x continuous at x equals 3? So f of x equals x is this linear function here, which we can tell by looking is going to be continuous everywhere, right? I can draw a line without lifting up my pencil, but we're just going to go through the motions here. So particularly, are we continuous at x equals 3? So there are 3 things to check. Number 1, does f of 3 exist? So can I plug 3 into x and get out a value? Yes, I can go ahead and substitute 3 in for x, and what comes out is 3, because x is the identity function. So f of 3 equals 3. Perfect. So kind of looking at the graph, when I plug in 3, I get out 3, so I'm defined. Does the limit as x approaches 3 of x exist? So looking at the graph, as I get close to 3, on both sides of 3, I do get closer and closer to the same number. The number I get closer to is 3. So number 2, does the limit as x approaches 3 of x exist? Yes, it does. So it exists and it equals 3. So then part 3, does the limit as x approaches 3 of x equal f of 3? In other words, do part 1 and part 2 equal the same number? And you'll notice that they do. So 1 and 2 are the same value. The function value equals the limit value, and they're both 3. So I've satisfied all 3 parts to the definition. So yes, f of x equals x is continuous at the point x equals 3. So it's not always going to be the case that a function is continuous, and when it's not, then we say it is discontinuous at a particular point. So if a function f is not continuous at a point c, then we say that f is discontinuous at c, and that c is a point of discontinuity of the function f. So informally, a point of discontinuity is a break or an interruption in the graph, so at a particular x value. So in this next example, we're going to look at a piecewise function that actually happens to be discontinuous. So the question is the following piecewise function continuous at x equals 2? So the piecewise function is 5 minus x squared when x is less than or equal to 2, and x minus 5 when x is greater than 2. So we don't know yet that it's discontinuous. We're going to have to show that. We're going to have to try to determine if it is continuous at 2, and then find an error in one of the 3 parts we need to check. So is f of x continuous at 2? First, we decide if f of 2 exists. So we have to try to plug 2 into this function. Well, this function here is only defined at 2, so it's less than or equal to 2 for the top function. So I have to substitute 2 into 5 minus x squared. So 5 minus 2 squared, 5 minus 4 is 1. So does f of 2 exist? Can I get out a value when I plug in 2? Yes, I get out 1. So f of 2 exists. For the second part, I need to decide if the limit as x approaches 2 of f of x exists. And here, I have to actually take and consider 2 limits, the limit from the left and the limit from the right, because 5 minus x squared is for values less than 2, so from the left of 2, and x minus 5 is for values bigger than 2, or to the right of 2. So in order to evaluate these limits, let's go ahead and take a look at the graph. So this is a piecewise function that we should be able to graph. So here's the piecewise function. So this parabola is 5 minus x squared, and then this line is x minus 5. So as I approach 2 from the left, I'm getting closer and closer to 1. So the limit as x approaches 2 from the left is 1. And as I approach 2 from the right, my y values are getting closer to negative 3. So since 1 does not equal negative 3, the limit from the left doesn't equal the limit from the right. So that means that the limit as x approaches 2 of f of x does not exist. And once we find one part to the 3 parts that fails, we can just stop. So we don't have to check the third condition. We already found one that fails, and we have confirmed that the function is discontinuous at 2. So the graph, right, confirms that we don't have continuity, because if we think about drawing this thing, if I start off to the left here and I trace this function, I don't have to lift my pencil up until I get to 2. At 2, I have to jump down and then continue drawing the rest of my function. So I am discontinuous at the point 2 on this piecewise function. Now, it is also possible to have one-sided continuity at a point. So a function f is called right continuous, or continuous from the right, at a point x equals c in its domain if the limit as x approaches c from the right of f of x equals f of c. So if the limit from the right equals the filled in value, equals the defined function value. And a function's left continuous, or continuous from the left, at x equals c if the limit as x approaches c from the left side of the function equals the function value. So if that's where the filled in circle is. So taking a look at this graph here, let's consider the limit from the left side of 2. So the interesting point here is 2. So the limit as x approaches 2 from the left-hand side. So as I approach 2 from the left, well, I'm getting closer and closer to 1, and I happen to equal the function value at 2. That's where the filled in circle is. So the limit as x approaches 2 from the left of this function, f of x, so that equals 1, which also equals the function value itself, f of 2. So since I approached from the left-hand side, and I got closer and closer to 1, which happened to also be the function value, this is considered to be left continuous. Because as I approach from the left side, I approach the function value. So f is left continuous at x equals 2, but let's take a look at what's happening from the right side of 2. So as I approach 2 from the right-hand side, then my limit from the right-hand side is going to be negative 3. As I get closer and closer to 2 from the left, I get closer to a y value of negative 3, but the limit value doesn't equal the function value. The function value is up here at 1, so there's no way it can also be down here filled in at 3, or else it wouldn't be a function. So f is left continuous at x equals 2, but not right continuous. So in general, a continuous function is defined to be one that is continuous on every single point of its domain. So is it feasible to test every single point on the domain of a function? No, it's definitely not. There are infinitely many points on most of the functions that we'll deal with. So this list of known continuous functions is one that you'll need to commit to memory, because these are the functions that we primarily deal with, and what's nice is that this list of functions are all continuous for every single point in their respective domains. So polynomial functions are always continuous on their domains, and their domains are all real numbers. Nth root functions are continuous on their domain. Rational functions, trigonometric and inverse trigonometric, exponential functions, and logarithmic functions. So all of these functions, these types of functions, are continuous on their domain. So there's no need to check them from now on. We can just assume that anytime we come across one of these functions, that they are a continuous function without proof. So now let's look at the types of discontinuities. So the first type of discontinuity is called a removable or a point discontinuity. And formally, this happens when the limit as x approaches c of f of x exists, but f of c does not exist. So the actual function value is missing, or the limit doesn't equal the function value. And then we say that f has a removable discontinuity. So taking a look at these two examples, as I approach 2 in each of these examples, the limit exists. So as I approach 2 from both sides, I get closer and closer to this y value of 2, both times. However, if I were to try to draw this graph without lifting my pencil, I'd have to I'd have to jump over this little hole here. So there is one point that has been removed, right? So that's why it's called a point or removable discontinuity. So it's been removed altogether here, and then on this graph, the point has been removed and then put somewhere else. So in each of these cases, I have what's called a removable or a point discontinuity. The next one is an infinite discontinuity, and this happens if one or both of the one-sided limits does not exist or is infinite. So then we say f has an infinite discontinuity. So here, infinite discontinuities on a graph represent vertical asymptotes. So at the x value of a vertical asymptote, in this case 0, I would be drawing my function, but then I'd have to lift up my pencil and then move up in order to keep drawing it. So once I had to lift up my pencil at that point, that's where I have my infinite discontinuity. So on a graph, it's a vertical asymptote. Removable discontinuity on a graph is a hole. Is a hole in the graph versus a vertical asymptote. And then there are two more types of discontinuity. We can also have a jump discontinuity. And this happens if the limit from the left doesn't equal the limit from the right. Then we say that f has a jump discontinuity. So on this graph here at 0, the function has a jump discontinuity. So the whole function jumps up here. If I were to try to draw this without lifting my pencil, I'd have to stop at 0 and then jump up to continue the entire graph. So a jump discontinuity is when the whole function jumps up, rather than just that one individual point being removed or relocated. So here we have this jump discontinuity. And then finally, if the function oscillates too much, then we say f has an oscillating discontinuity. And this one's pretty rare. And in fact, we can't have a function oscillate too much and be considered continuous, because remember that this is one of the ways for a limit to not even be defined. So here at 0, or a limit to exist, so here at 0, the limit can exist. So if the limit can exist, there's no way we can think about continuity, because continuity depends on the limit existing at a particular value. So oscillating is another type of discontinuity, but one that we rarely focus on. And now we're going to take a look at the laws of continuity. So assume that f and g are continuous at the point x equals c. Then the following functions are also continuous at c. So basically, if we have two continuous functions, then the sum of those functions and the difference of those functions are also continuous. We can multiply that function by any constant k, and it will still be continuous. We can multiply and divide the function, and it will still result in a continuous function as long as the denominator here is not 0. And then we can take the function and raise it to a power, or take the nth root of it and still get a continuous function. And now we have three more properties involving continuity that are heavy on the notation, so I really want you to focus on the title of each one, because that really tells you what's going on. So the continuity of composite functions. So composite functions, we should think composition of functions, so one function inside of another function. So this theorem says that if g is continuous at x equals b, and f is continuous at g of b, then the composition f of g of x is continuous at b. So what it's really saying here is that if we compose two continuous functions, the result is going to be continuous. The next theorem says that there is continuity of inverse functions. So if f is continuous on some interval from a to b, with range R, and if the inverse exists, so just a quick reminder, inverse is we switch the domain and range, we switch the x and y values, then f inverse is continuous on its domain R. So notice that f was continuous on an interval from a to b, and the range of the original function was R, and then the inverse function is continuous, and now the domain, so the range and domain switch, so the domain is now R. So again, focusing on the title, inverse functions are also continuous functions. And then finally, limits of continuous composition of functions. So if g is continuous at some point b, and the limit as x approaches c of f of x equals b, then the limit as x approaches c of g of f of x equals g of the limit of f of x equals g of b. So what's happening here? What's really happening, if you kind of focus on this last part, is that we can pull this limit into the composition. So the limit of g of f of x became g of the limit of f of x. And then the limit of f of x is b, so this portion here got replaced with a b, and that's where this g of b is coming from. So as long as g was a continuous function, and the limit of f of x equals b, then we can pull the limit into the composition. So again, in the title, the limits of continuous composition of functions holds to be true. So now we have all of these properties that apply to the continuity of particular functions, so let's see how we would use them. So in this example, we want to decide whether or not tangent of natural log of x is continuous at x equals 1. So if we look at this function, this is a composition of functions. So the inside function here is natural log of x. So we'll go ahead and say that f of x is natural log x, and g of x is tangent x. So what this function is it's g of f of x. So in our properties, we know that the composition of continuous functions is continuous as long as we can plug the values in. So first, each of these functions is continuous on its domain. So natural log is a logarithmic function which is continuous on its domain. Tangent is a trig function which is continuous on its domain. So we just have to make sure when we substitute 1 into this that we're going to get out a number, that it's going to make sense, that 1 is in the domain of this composition. So tangent of natural log of 1, so natural log of 1 is a value you should know, it's 0. So what this is it's tangent 0. And we can do tangent 0. Tangent 0 is just 0. So 1 is in the domain. So here, natural log is one of the known continuous functions. Tangent is one of the known continuous functions. So is tangent natural log x continuous at x equals 1? Yes, it is. So we're using our known continuous functions and the fact that this is a composition of those continuous functions, and the fact that 1 can be substituted into this and still make sense, that tells us that yes, this is continuous at x equals 1.